Well, hello everyone and welcome to our calculus notes for section 2.1. Today we're going to be talking about the tangent line problem and the limit definition of the derivative. So first off, let's talk about a tangent line. It says a tangent line to a curve at a given point is the straight line that just touches the curve at that point. So we're going to take a look at an example of some tangent lines here. And in this graph right here, we can see the tangent line moving across the graph at different x values. So you can see that it's just touching the graph at the single point, and it's equal to the slope of the graph at that point. So here it's positive, here it's 0, here it's positive again. The slope would be 0. Now it goes to negative. Here it's at 0, now it's positive again. And then negative, and switching back to negative there. So what we're going to do is draw a couple of these tangent lines and practice doing this. And then we want to label the slope as being positive, negative, or 0. So right here at this first point, we want to draw the tangent line right across here. Okay, so we're just going to draw a line straight that's just touching. Now that one is going to have a 0 slope because it's horizontal. So I'm just going to write m equals 0 there. If we come over to our next point right here, if we draw that tangent line, let's just be careful. We come and we just barely touch the curve, and then we get the line right there. So in this case, our slope is going to be positive. So I'm going to say m is positive. Okay. Now if we look at our next one, at this point, let's go ahead and try to draw that. So it comes in and just touches, and our slope is still positive here. Over at this point right here, if we draw that tangent line, this is kind of an odd place because we're actually going to start on top of the curve here, and it actually goes through the point. Okay, through the point of tangency, and it comes out the other side. And so sometimes the tangent lines can do that, but we want to be as close to that curve as we can. And here we would have a negative slope. And then this one down here at the bottom, again, would have a slope of 0. So that's kind of how you draw some tangent lines to a curve. Now, what we're going to do is figure out how can we define this line. So to define a line, you need two things. Number one, you need a slope, and number two, you need a point. So we're going to be talking a little bit more about these tangent lines, and we're going to look at figuring out how do you find the slope, and then how do you find the point. So to define a tangent line at a point P, you need to find the slope of the tangent line at the point P, and you can approximate the slope using a secant line through the point of tangency and a second point on the curve. So I'm going to go ahead and just draw a curve here. We're going to call this f at x, and we're going to talk about the point of tangency at this point right here. Okay, so we're going to go ahead and draw that tangent line to the curve right there. Okay, so this is my tangent line. And so what we're going to do is first try to figure out what is the slope of this tangent line. So let's just talk about slope for a second here. Slope is something we've dealt with in the past, and so we know a few things about it. Sometimes we call it m. Okay, we used m in Algebra 1, and we had a slope formula. And what that formula was y2 minus y1 over x2 minus x1. Okay, now what that meant to us graphically was some sort of rise over run. Okay, so vertical change and horizontal change. Rise over run gave us our slope. Now we're going to clarify this a little bit more for our purposes today, and we're going to call the rise, or y2 minus y1, we're going to call that delta y, which is the change in y. Now the run, or x2 minus x1, we're going to call delta x, or the change in x. Now as we get closer to talking about calculus, this is going to become dy over dx, or the derivative of y with respect to x, which is basically the slope of that tangent line. So what we're going to do is figure out the slope of the secant line and then make better and better approximations to figure out the slope of that tangent line. So what we're going to do is just kind of pick any point that's not on the point of tangency, and then we're going to draw a secant line through these 2 points. Okay, so here's my secant line. Okay. Now, when we go to find the slope of a secant line, our formula is basically going to be that y2 minus y1 over x2 minus x1. But we're going to do it more specifically, and we're going to use function notation. So let's kind of see where everything is here. So I'm going to call this C. This is the point of tangency. And we have this point C, comma, f at C. So that's where that is. The C is the x value, the f at C is the y value. Now for our secant line over here, we have another point, and it gives us another y value. And what we do is we actually move a certain amount away in that horizontal direction. And we call that amount delta x, or the change in x. So my x value over here at the secant line is going to be c plus delta x, because we're delta x away from c. All right, now if we try to find the y value of the point on the secant line, okay, that's going to be this length right here. And what we call this length is delta y. And so what happens is we're going to get this point as f at c plus delta x. So in other words, we're going to take that x value where the secant line goes through, we're going to plug it into my function, and that gives me the y value there. Now, delta y can also be written then as f at c plus delta x, okay, which is the y value up here at the top, and then minus f at c, which is the y value down here at the bottom. So if we're going to try to find rise over run, or y2 minus y1 over x2 minus x1, we are going to get the slope of the secant line to be f at c plus delta x, which is my y2, minus f at c, which is my y1, and then that's going to be divided by, well, let's see, we have c plus delta x minus c, and so really it's just going to be over delta x, or that change in x. So that's kind of the formula that you're going to use to figure out the slope of the secant line. Now, eventually what we want to do is figure out how to find the slope of the tangent line. Okay, so this is the basic situation we have so far. We have a tangent line here in black, and we have the secant line, which is approximating that tangent line. And so what we're going to do in order to figure this out is we're actually going to bring this point of the secant line closer to the point of tangency, so that eventually that secant line is going to really do a good job approximating the slope of that tangent line. Okay, and so when we think about what's happening here is we're actually shrinking that delta x, and we're letting it get closer and closer to 0. So you can notice as that delta x gets smaller, the slope of the secant line is getting closer and closer to the actual slope of the tangent line. Let me see that there. So what happens is if that secant line gets right on top of that point of tangency, all of a sudden we get something that is going to be undefined. Now the reason it's undefined is you're dividing the slope of the tangent line, you're dividing by delta x. So if delta x becomes 0, then you can no longer find the slope. And that's what makes finding the slope of a tangent line so difficult, is you only have the one point on a curve. So we can see what we're going to have to do is use a limit and find the limit as delta x approaches 0, and that's going to narrow right in on the actual slope of the tangent line. Okay, so essentially what we're going to do then for the slope of the tangent line, we'll call that m tan, we're going to get the limit as delta x approaches 0 of basically the slope of that tangent line. So f at c plus delta x minus f at c, all divided by delta x. All right, and that right there is going to give you the slope of any tangent line. Now, remember we said to define a line you need a slope and a point. And so this is how you find the slope. And next we're going to talk about the point and how you're going to actually find that tangent line. And so this is going to go right back into what you learned in algebra. You have your slope, and if you use the point slope form, you can come up with this equation right here, and that will give you the equation of that tangent line. So just thinking about what we talked about here, we're trying to find the slope of a tangent line here at point C. And so to do that, we are going to start off just by thinking about the secant line through this point right here. And what we have is some distance. We're going to call that distance delta x. Okay? And so that would give us a pretty bad approximation. And so what we're going to do is we're going to move that tangent line a little bit closer. Okay, we're going to move that secant line closer to the tangent line. And so that delta x now is a little bit smaller. Okay? It's a little bit smaller. And we're going to keep doing this approximation technique. Okay? We'll go pretty close there. Okay? So here delta x looks like it's only about that long. Okay? And so eventually we're going to be able to narrow in on the exact slope of the tangent line as we let delta x basically shrink down to nothing. So when we talk about the slope of the tangent line, we're also talking about the slope of the graph at the point. And so this is going to be an instantaneous rate of change, and it's going to be extremely important to be able to find these slopes. So we want to do an example now where we find the slope of the tangent line to the graph of f at x equals x squared plus 1 at the point -1, 2, and then we want to give the equation of this tangent line. All right, so here's kind of where we're looking. So -1, 2 would be the point right here, and we want to find the equation for this tangent line right there. Okay, so we need to find the slope, and we already are given the point, the -1, 2, right there. So in order to find our slope, we're going to use the limit definition. So slope of the tangent line, okay, remember, is going to equal the limit as delta x approaches 0 of f at c plus delta x, that's our y2, minus f at c, and then all divided by delta x. Okay? So this here is our limit definition of slope. All right. So what we're going to do first is just perform some substitutions. And instead of using the generic function notation, we're actually going to plug and substitute c plus delta x into my function. And then I'm going to substitute c into my function. So this will continue, and this equals the limit as delta x approaches 0. So first off, we're just going to deal with this first part, this f at c plus delta x. So we're going to take that c plus delta x and substitute it into our function for x. And so I'm going to get c plus delta x squared plus 1. Okay. Now I'm going to take the c and I'm going to substitute that in for x right here. So I'm going to have minus, this is going to be c squared plus 1. This is all going to be over delta x. Okay. So what I did here is I substituted into my function using c. Now, in this case, c is going to be a specific thing. So this is really the point c comma f of c right here. And so I can really replace that c value with the value that we have. So c in this case is -1. At this point, we're just going to go ahead and simplify everything. Okay? So in my next step, we have to rewrite the limit as delta x approaches 0 because we haven't taken the limit yet. And so when we do this, we're going to square the binomial here first. And so that's going to become 1 minus 2 delta x, and then plus delta x squared. All right, so that's the square of the binomial. Next, we still have that plus 1 right there. Okay, so this is that entire part in these brackets right there. Now we need to subtract f at c. And so we could perform the -1 squared plus 1, and that would equal 2. Or you can just come up here, f at c is equal to 2, because they gave that to us. At any rate, this is going to be -2. And this is all going to be divided by delta x. Now we're going to simplify a little bit more. So inside here, I'm going to combine my constants. So I do need to rewrite the limit as delta x approaches 0. And now I have 2 minus 2 delta x plus delta x squared, and then minus 2. It's all divided by delta x. And we can simplify a little bit more now. So this 2 right here and that -2 are going to cancel out. So we're left with the limit as delta x approaches 0 of -2 delta x plus delta x squared. This is all going to be divided by delta x. So what we did in this entire step, we simplified. And so we just used all the algebra skills that we've been learning up until this point. And one very important note that when you simplify, the constants in the numerator will zero out. And it's extremely important that those do zero out. You're going to see why in a second. Now, when we were talking about limits, remember we used a thing called direct substitution. And so the idea was that you can take that 0 and then substitute it in for delta x, and you should be able to calculate the limit. But in this case, notice what happens. If you plug 0 in for delta x, you would get 0 divided by 0. And we learned that's a hole in the graph and a removable discontinuity. So we're going to be able to remove the factor that's causing the issue. And in this case, the factor that's causing the issue is delta x. All right? And that's why when you slid that secant line all the way on top of the tangent line, you had that undefined slope. So what we're going to do is our process of factoring and canceling. So we can say the limit as delta x approaches 0. Well, let's factor out the delta x in the numerator. We're left with -2 plus delta x. That'll be divided by delta x. And at this point, we can cancel, and that becomes 1 over 1. And if I just rewrite this now, I have the limit as delta x approaches 0 of -2 plus delta x. All right, Now at this point, the denominator is gone, and so we are able to use direct substitution. And so we can just substitute 0 in for delta x, and we get -2 plus 0, or -2. All right, so just to recap, in this case, we tried direct substitution, and that failed. So we did the factor and cancel until we could use direct substitution. So what did we just find here? Wow, we got to go all the way back to the beginning. We were looking for the slope of the tangent line, and here it is. The slope of the tangent line is -2. And so we can write that right here. The slope of the tangent line equals -2. Now that's good because it kind of looks like -2. What we're going to do at this point is actually find the equation of that tangent line. Okay, so what we have is we have a slope of -2, and then we have a point, and that point is -1, 2. That's the point of tangency. So if we use our guide up here, it says y equals m times x minus c plus f at c. So we're going to write that here. Y equals m times x minus c plus f at c. All right, so let's go ahead and substitute so we can find that tangent line equation. M equals -2, x minus, well, remember the c value is -1. All right, that's our c value right here. And then f at c is 2. And so we're just going to go plus 2. And now we're just going to simplify this. So we get y equals -2 times x plus 1, and then plus 2. We can distribute the -2 and get -2x minus 2, and then plus 2. And we'll simplify the constants and get y equals -2x. So we know that the tangent line through the point -1, 2 is equal to y equals -2x. Now, that was a really, really long process. And the idea is we're going to want to eventually figure out what is the slope at any point. So what's the slope when x equals 1? What's the slope when x equals 2? What's the slope at -2? Or really any point along here? Well, to find each one of those things, you would have to go through this whole entire process. So what we're going to do is now just take a look at this definition and then think about what we did here before we plugged in the actual point and see if we can't figure out an equation that will give us the slope of the tangent line at any x value. And that's what we're going to talk about next.